Thank you. So our next speaker is Sheng Meng. Actually, I'm confused where I'm from. So at the moment you are from Kias, right?
Yeah.
In Seoul. And since our workshop is small but very up to date, we have the most recent results reported here, and you can notice that Sheng Meng's talk is based on at least partially based on the result which appeared on the archive just today in the morning. So we have the most fast delivery of good results to our workshop. So Sheng Meng will tell us about Jordan property for varieties. Thank you.
Okay, thank you very much for the invitation. Yeah, initially I just want to survey some basic previous known results and techniques. But until very recently, we are lucky to have some new discover. So, okay, let's start. So today the talk consists of 4 parts. First, I will review some basic knowledge of the Jordan property, and then I will recall some early results on projective and killer varieties. Part 3 and part 4 will be. Part 3 and part 4 will be my the main purpose of this talk. Which for 3 I will study the finite subgroups of the automorphism group fixing some subvarieties. And finally, I will show the Jordan property for automorphism group of Fujita's class. Okay. So a group G is Jordan if it has almost a billion finite subgroups, which means precisely there is a Jordan constant J such that every finite subgroup H has a billion subgroup H1 with index bounded by this Jordan constant. It is named after by Camille Jordan, who proved the famous theorem in 1878 that the general linear group is Jordan for any field K of characteristic 0. And as a simple exercise, you can see that characteristic 0 is important, for otherwise it is not true. You can show that the GLN of the field algebraic closure of the finite field FP is not Jordan. Here are some purely group exercise. We consider the exact sequence of groups, and first we see that if G is Jordan, then the subgroup is always Jordan. Second, if G2 has bounded finite subgroups, which means that there is a constant, any finite subgroup of G2 has order bounded by this constant. Then we call it has bounded finite subgroups. And together with G1 being Jordan, then we can show that the extension group G is Jordan. Third, if we have G1 being a finite group, and the middle one is Jordan, then the image G2 is Jordan. Fourth, if G1 has no non-trivial finite subgroups, and G2, sorry, let me change another. This one I cannot. Okay. Okay. Share this one. Okay. Okay. So fourth, if G1 has no non-trivial finite subgroup, for example, if G1 is a unipotent group and G2 is a Jordan group, then the extension is still Jordan. And if G splits as the product of the first and the third, then and G1, G2 being Jordan can imply G is Jordan. The first 5 to the 5th, the proof are quite simple, about few words maybe. And the 6th is still fundamental, but the proof may take several lines. It says that G1 has bounded finite subgroups. G2 is Jordan, and G2 and all its finite abelian subgroups can be generated by at most m elements. Then the middle one is still Jordan. We are not. We are only use first and second and maybe first, second, and fourth throughout this talk. Okay, so our so why we have so many lemmas? Because in general, the extension cannot preserve the Jordan property. There are examples, and I will show it in the next slide. Before that, I would like to recall another important theorem by Minkowski. So it says that the GLN of the rational field has bounded finite subgroups. So with this theorem, we can look at and together with the second property, we can look at the rational representation of G, and then to show the Jordan property of G is we only need to show the Jordan property of G1. Okay. Okay. So okay. So now let's look at what the general question look like. The question is asked by Popov that is a automorphism group of a variety being Jordan for an algebraic variety or a complex space. This question cannot be the assumption in this question cannot be vacant, because Popov himself showed that there are non-Jordan automorphism groups of connected non-compact complex threefolds. So here, the assumption compact here cannot be vacant, and the complex manifold can also not be vacant to real manifolds because there are non-Jordan diffeomorphism groups of compact real manifolds. And the automorphism here cannot be vacant to by meromorphic automorphism groups, because Popov showed that Popov showed that for algebraic surfaces, the birational automorphism group of S is Jordan if it is not isomorphic to a product of a projective line and an elliptic curve. And then Zahin showed that the birational automorphism group of P1 cross E is not Jordan. So here we have the exact sequence, which gives an example of previous question. Okay, so first we look at the large group birational automorphism of P1 cross E. Then it descends via the ruling to the automorphism of the elliptic curve, and the kernel is the automorphism of a projective line, with the base field being the function field of the elliptic curve. And you can verify that easily that this group and the image auto E is Jordan, but the extension group is not Jordan. Okay, any question? Okay, so okay, there are several non-lower dimensional.
Okay. Another question then as a comment. So in the question of Popov, a reasonable question is you can reasonably reformulate it for just yes. So sorry. Yes, sorry. Maybe I have no comments here. Thank you.
Oh, okay. Let's move on. So there are several known results, but very few results on the lower dimensional cases. Okay. So first, the surface case is still okay. The Badman and Zahin, they proved that for an algebraic surface, it has Jordan automorphism group. And Prokhorov and Sharomov, they proved the Jordan property for the automorphism of a compact complex space for the surfaces case and the Moshe's threefolds. Okay. Okay, but in higher dimensional, there are also we researched on the automorphism group, and it is known for the projective case and the compact Kähler case. The projective case is done by me and Deqi Zhang, and the Kähler case is done by Kim using a similar idea. Here I'll sketch the idea of the proof using the algebra group. First, we look at the rational representation on the second singular cohomology. And by the Minkowski's theorem, this group has bounded finite subgroups. And we write down the simple exact sequence and denote by the kernel by auto-Tor. This group is very important. Okay, auto-Tor X, which is the kernel of this rational representation. So as the third group has bounded finite subgroup, we only need to show that the kernel auto-Tor is a Jordan group. Okay. Then we look at the neutral connected component of the automorphism group, and we denote it by auto-0. Since it's connected, and so it has no non-trivial rational representation. So in particular, it is a subgroup of auto-Tor X. Then we fix a Kähler class since we are working on projective manifold and Kähler manifold. So we can fix the Kähler class and denote by auto omega by the subgroup, which preserving the class. And by definition, we see that it contains a group auto-Tor X. Here we use the embedding of the H11 to the H2 XR. Then by a famous theorem by Lieberman and Fujiki independently, they prove independently that the index of auto omega and auto 0 is a finite has finite index. So together, we see that the quotient group auto X and auto 0 has bounded finite subgroups. And then we see that we only need to show that this group auto 0x is Jordan. So now we now move to auto 0x. It is a classical result of a Grothendieck that if X is projective, then auto 0x is a connected algebraic group. And Duodie later showed that if X is complex, then auto 0x is a connected complex Lie group. There are now known two different methods to show that this group is Jordan. One way is to use the Rosanlik decomposition, which is written as G equals to G affine and G anti-affine. Here, G affine meaning the maximal normal linear subgroup of G, maximal normal connected linear subgroup of G, and the G anti-affine is the minimal connected subgroup of G, making the quotient being linear. So in particular, the G anti-affine is contained in the center of G, and making this commutativity, we can show that G has almost bounded commutator groups of finite subgroups. Precisely, it means that every finite subgroup H has a finite subgroup H1 with the index bounded such that the commutator group has bounded order. Okay, I will not go into too detail of this argument. I will mention about another later approach made by Popov. He simply proved that the real finite dimensional connected Lie group is Jordan. The idea is simple. First, he considered a maximal compact subgroup of G, and note that maximal compact subgroups of G are all conjugate to each other. So this argument implies that. If you fix a maximal compact subgroup of G, then it contains all conjugate isomorphic copy of finite subgroups of G. Then it is known that the compact Lie group admits a faithful finite dimensional representation. So in particular, you can embed all the finite subgroups of G into one general linear group. So in particular, G is Jordan. Okay, so this is roughly the proof of the automorphism group of projective and Kähler varieties being Jordan. Any question? Okay. The Jordan property is also highly related to another boundedness called about the almost fixed point. And using this, and also the boundedness of the terminal final varieties, which is the so-called BAB conjecture proved by Bika. And using this, Prokhorov and Sharomov, they showed the Jordan property for the birational automorphism group for any rationally connected unfold. And even further, the Jordan property for the birational automorphism group of any variety with irregularity equal to 0. This is H10. In particular, the criminal group is Jordan. I will only talk about the almost fixed point technique, which will be used later. The key idea is to reduce the second to the first by taking the maximal rational kinetic fibration. Then we show that any finite subgroup G has an almost fixed point on some model of rational kinetic variety X. It means that the almost fixed point is defined precisely in this way. So there exists some subgroup H of G with index bounded such that H has the fixed point. Alternatively, you can say that G admits an isotropic subgroup with index bounded. Okay. In this way, if you find such H, then we have the following well-known lemma that H admits a faithful representation to the tangent space. So you can have the tangent map from H to the automorphism of the tangent space at the point X. Since H is finite, this tangent map is injective. In this way, you can see that almost fixed point implies the Jordan property, and the Jordan constant can be controlled by the bound of almost indices and the Jordan constant of the general linear group. The converse does not hold. It means that Jordan property cannot imply the almost fixed point. For example, you can simply consider the elliptic curve and the translations over the elliptic curve. Then it never have a fixed point unless it is the trivial identity map. Indeed, but however, the converse holds true for irregularity equal to 0 case by considering the MRC fibration, and the following stronger results by Prokhorov and Sharomov. By looking at the birational automorphism of the base of the MRC fibration, they show that the base is non-unirod, and the birational automorphism of the non-unirod and the Qx equal to 0, it has even bounded finite subgroups. Okay. So this is roughly several early results. Any question? Okay, so now let's move to now let's try to generalize the idea of the almost fixed point to show the Fujikis class. First, our setup is now a connected complex manifold, and let there be also a connected complex submanifold. We denote by we denote by auto xz the subgroup of auto x such that the gz equals to z. And recall that if z equals to x is a point, then we have such tangent map. while the kernel has no non-trivial finite subgroups. Okay, we also need to consider the following automorphism group subgroups. So first, let E be a vector bundle of Z and denote by auto E to Z the bundle automorphisms, meaning that the automorphism of E, which is equivalent, which can be descended to an automorphism of Z, and so it maps fibers to fiber, and moreover, it maps the fiber linear to a fiber. Okay, so we consider this subgroup. Okay, then we consider the very simple tangent the fundamental sequence. So here, TZ is the tangent bundle of Z, and this one is a tangent bundle of X restricted on Z. And the third one, the quotient, then will be the normal bundle. And we can consider the tangent map, the induced tangent map. Then we get a natural normal map from the automorphism of X fixing Z to the automorphism of the normal bundle from this commutative diagram. Okay, so then we try to show that the kernel of this this homomorphism has no non-trivial finite subgroups. The idea is simple. We first pick some G in the kernel with finite order, and then by definition, it means that this one, the third vertical is identity. So in particular, its restriction is descending to the base Z is also identity. It has the tangent map is also identity. So the first and the third arrow are identity map. Then this implies that the middle arrow is a unipotent action for each point. Z lies in Z. Note that G itself is a finite order, so the middle one here, it also has finite order. So in particular, it is semi-simple, and together with unipotent, it means that it is also identity. Now we find the fixed point Z. Now G has a fixed point Z with the tangent map being identity. So this implies that by the previous lemma, it implies that G is identity. Here, we need the X being connected.
Sorry, and can you repeat once again? Can you show the previous slide once again?
Sorry. This one?
Yes. So how do we? Can you explain maybe informally what's going on here? So here you replace X by some kind of a neighborhood of Z, right?
No, not neighborhood of Z. Simply, this group simply means the automorphism fixing this Z. G maps Z to Z itself.
Yeah. Thank you. But then, so you have two groups here: the stabilizer of Z, which is out XZ, and then the automorphism group of the total space of the normal bundle. So
yeah, you have the. So this is okay, right? Mm-hmm. This morphism is okay, right?
Yeah, I think I understand. I think I understand what's going on. Thank you.
Okay. So yeah, this is just the bundle version of the previous previous one for the almost a fixed point Yeah. Okay. Previous one is this one. Is this embedding?
I see.
Okay. Yeah. This is, you can say this is the normal bundle of the point, right? Okay. So. Okay. So sorry. Okay. So indeed, the proof of indeed this step also use the previous technique about both it is unipotent and it is semi-simple. Then it implies identity. Okay, so we use this technique twice indeed, but on different space. Okay, you can consider the pullback action. You can consider the induced action on the stock of this point, and then you can look at the infinite dimensional representation, something like that. Yeah. This is also you can also apply the Cartan's locally representation of finite group with a fixed point. Okay. So now what next? Because previously we know the result for the projected and the compact scalar, so we need to do some compactification. But now our bundle is not compact, so we first let E be the normal bundle and O Z cross C simply the trivial line bundle of Z. And we consider the T, which is a one-dimensional complex torus, act on the vector bundle E and O by the natural scalar multiplications. So the action is simply by sending the vector V to TV. And then there is a natural T equivalent monomorphism phi. So first you have this G, and then you have this factor. You have this factor. This we keep it here, but for the second factor, we only keep the descended automorphism on Z, but on the vectors it is always identity. Then we have the this is something like the embedding of the general linear group GLN to this is maybe I can sorry. Okay, so this is something like the embedding of the GLN, general linear space, to the PGLN plus 1. Okay. Then we have the following this kind of equivalent commutative diagram. So we already know this too. The third one is the natural quotient of the vector bundle E plus O, and the equivalency is because of the scalar action commutes with any matrix. So it is equivalent, and we know that this natural quotient is a PR bundle over the base Z. Then we look at the homomorphism of this projectivization psi. This is induced by simply take the T quotient, and of course it may not be injective, but if we consider the composite, then it is still injective, because you can see by the natural T quotient, the kernel of psi lies in the diagonal scalar matrix, diagonal scalar matrix. But the image of this one, you see it all. The second factor is always identity, so it is always 1. So you can see that the kernel of this composition is still trivial, so it is injective. In particular, we have an equivalent compactification of the vector bundle E to the projectivization of E plus O. Okay, this is the bundle version of the general linear group GLN to the PGLN plus 1. Okay, then we have the following result. So recall our setting. X is a connected complex manifold the connected complex submanifold auto XZ is Jordan. To show this is Jordan group, it suffices for us to show that after projectorization, this projective bundle has Jordan automorphism group. So as a corollary, if we are lucky to find some compact Kähler Z, then we see that in this case, if there is a compact Kähler, then the PR bundle of a compact Kähler is still compact Kähler. So in particular, we know that compact Kähler has Jordan automorphism group. So this is Jordan, and we have auto XZ is Jordan. Okay. Any question? Okay, so now we have finished our study of auto XZ in this section. So now let's come to our first section. Okay, now let me state the main result. First, recall that Fujikis class C means that complex spaces which are meromorphic image of Kähler manifolds. Our main result, which is the joint work with Fabio Peroni and Deqi Zhang, we eventually proved that the automorphism group of Fujikis class is Jordan. Before begin the proof, I would like to state several important remarks. First, we can always use the Hironaka's equivalent resolution to assume that X is always smooth. And second, we can assume that X is connected because the compact manifold has only finite components. Third is the most important. Previously, we tried to use the Cho's lemma, which says that there is and together with Cho's lemma, which says that there is eventually a projective biholomorphic map from a Kähler manifold to our X. But however, we cannot show that this pi is auto X equivalent. And later, I will show that why it is difficult here.
Sorry, and can you comment on the first remark? Apparently, all the resolutions are, after all, due to Hironaka, but the equivalent one, isn't it due to Birston and Milman?
Oh, I forgot. I only remember something like.
Is it really in the original Hironaka's?
Anyway, it is blow up the singular locus. If the singular locus is not smooth, you blow up the singular of the singular, something like that. Yeah.
Yeah, but in fact, resolution algorithm is much more complicated than just blow up of singular locus. I think that we have to use some equivalent version of Hironaka, which is appeared.
Yeah, not that simple.
Much
yeah.
later. Yes.
Yeah.
That's of course it's known now.
Okay. If you are too worried about it, you just assume smooth because later we will not apply the resolution anymore.
So let me make a remark. Hironaka has a paper in 1970s published in Vietnam Mathematics Society. So I guess he has a proof. So if you are not happy, you can use a modern proof by this Polish mathematician start with W. It's very hard to read. So and
I see, but it's not accessible anymore. Anyhow, but
yes.
Also, I'm not sure. Does it contain analytic version, not only algebraic?
Yeah, it's analytical. Everything is a functorial. So there are many different versions. The Polish mathematician or Bielstone. There are two groups, right?
But this is quite recent. It appeared much later. Or color book recent also.
Color book also okay. Color book, I'm not sure whether it's analytic, but it's a functorial in the analytical case, so everything is okay.
Okay.
Thanks.
Anyway, if you are not happy about this, then you just assume it's smooth, because later I will not use resolution anymore. Okay. But the third part is I'm not very surprised about the first one, but the third one is quite difficult. And indeed, so this caused our first question about the equivalent Kähler model. A second question is from another different view. So previously, we showed that we can reduce the Jordan property for auto X to auto 0, but we need to show that the quotient of this group has bounded finite subgroups, or more precisely, this group have bounded finite subgroups. And by Lieberman or Fujiki, this group is even finite if X admits a Kähler form, but we don't know whether it is true for Fujiki's class. Okay, so these are either two of these. Either two affirmative answer to either of the two questions can give an alternative simple proof of our main result. So, okay, now let's start our proof.
Sorry, is it possible that the automorphism group of X tilde is larger than the automorphism group of X?
Of course, you can blow up P to a point. Maybe I think you mean auto X tilde is larger than auto X.
Yeah. So how do you connect the statements for X tilde?
Yeah. Oh, if it is equivalent, I mean, if it is equivalent, it means that auto X can be embedded into auto X tilde. Is this okay?
If it's larger,
so
it's okay.
Yeah.
The problem if it's smaller. For
Yeah.
that property.
Yeah. So here here the equivalency is important. It means that auto X equivalent. It means that it can every automorphism of X can be lifted to an automorphism of X tilde. So this is a subgroup of X. If it exists, it is a subgroup of auto X tilde. And
okay,
then you can, yeah.
So maybe the statement you prove is the statement for the subgroup automorphism of group. Yeah, the subgroup of this subgroup inside.
Yeah. This if this is Jordan, then its subgroup is also Jordan. Then done. Yeah.
Oh, thank you.
Okay, so we use our techniques use to find a good invariant locus called the non-Kähler locus. So let X be smooth, okay, in the Fujiki's class with a fixed Hermitian form omega. It is known that this is an alternative definition. Okay, there is a big 1-1 class alpha in the Bochum 1-1 cohomology, which means that we can write a T as alpha plus I partial bar phi greater or equal than epsilon omega, weakly in the sense of currents for some epsilon greater than 0 and the quasi-Poirot subharmonic function phi. And if such T satisfies this condition, we call T is a Kähler current contained in alpha. Then we define the non-Kähler locus, which is similar to the augmented base locus by taking the intersection of the singular locus of T, where T is a Kähler current contained in alpha. And here the singular locus of T is defined simply by the singular locus of the potential function phi. And the singular locus of phi is just the point where phi is not smooth. Okay. By a result of Buxton, it says that we don't need to take all the intersections. We can find one current T such that the non-Kähler locus is just the singular locus of this Kähler current. And furthermore, by the famous result of Demailly, fundamental regularization theorem for currents. It says that we can further require this potential function phi being written precisely as this form. Here C is a real constant, and H is a real function, smooth real function, and Fi are holomorphic function. All are in the local versions. So you can see that it is then easy to see the singular locus of phi being those points where the sum of square equals to 0. And now we let I be the ideal shift locally generated by these functions Fi. Then we can see that the ENK, the non-killer locus of alpha, is just the zeros, common zeros of these local holomorphic functions. Here I also put here the ideal shift is important because to obtain the Kähler model for the Fujita's class, usually we need to the key step is to blow up the ideal shift of I and then apply the choice lemma. However, later we will show that we will easily see that this non-killer locus is invariant in some sense. But however, the ideal shift may not be reduced, so we cannot show that the ideal shift is invariant. So here it makes a little bit trouble. Of course, you can blow up the non-killer locus. Try to blow up the non-killer locus to get a, but we don't know. It is equivalent, but we don't know whether it can. In this way, we can eventually, in finite many steps, we can get a killer model by simply blow up the non-killer locus.
Sorry, I have a question.
Okay.
Suppose, example, your variety is moisture zone.
Yeah.
And is it true that your non-carrier locus is just you have to take maybe
Big
some
divisor.
big divisor, and base locus some stable in some stable case, right? A stable sense, right?
Yeah, it is just for motion. I remember, I'm not familiar with this part, but I remember a result by Demai and Paul. Maybe they show that if the big divisor is also nef, then it is the null locus of this big divisor. Maybe, yeah. But if without nefness, maybe they are not the same.
It's not such a divisor do not necessarily exist. Nef divisor.
Yeah, may not be nef
But
divisor.
big divisor always. So.
Yeah, you may not find the nef divisor. So this may be a little bit larger, maybe, I guess. Not clear.
But they are related somehow, right?
Sorry?
They are related.
Sorry, I can't hear it clearly.
They are related somehow.
Yeah, they are analytic. Yeah.
Thanks.
Okay, because it is defined by the holomorphic, the several holomorphic functions, so it is a closed analytic subvariety of.
Oh, maybe the question was, suppose that again, suppose that X is moisture zone and choose a big bundle, and then it has a locus of like bad behavior. This big bundle, you can associate like something, like maybe if it is not nef, you can possibly associate to it the locus of covered by maybe curves with which it intersects badly. If it is nef, then you can also associate to it something. And is there any relation between this natural sublossi of X in the moisture zone case and what you define here?
If it is nef and big, then it is just the null locus of the big lump bundle. Yeah, just the augmented base locus. Yeah.
Augmented base locus. And if it is big but not nef, maybe something is contained in something. Like
I never see this result because this is also a famous result by Demai and Point. They assume nefness. Nefness is important. Yeah.
I see.
Okay.
Make a comment. I guess being there for not is a conjecture. I guess. It's not known. I guess it's still conjecture to be there for not. I guess.
Yeah.
Sorry, what does the conjecture say? I missed it.
You know, this bigger class you have the existence of a different bigger class on you know, of a Kähler current. You have Kähler current, but it's a bigger current, but may not be naive. So the existence of naive and bigger current in this Fujiki class C is not known. I guess it's
I see.
Yeah. This is another different. Yeah. Okay. So what we only need is it's about the non-killer locus, and you see that it's defined by the class. Okay, so it is well defined, and gives us several remarks and facts. So you see that if the non-killer locus is empty, it means that the single locus of T or phi is empty. So T is a smooth Kähler current and has further a Kähler form. So which means X is Kähler, and then we don't need to do anything. So we can always assume that the non-Kähler locus is not empty. Another factor is that since we take the non-Kähler locus, it is not a closed analytic subvariety, but luckily it is again lies in the Fujikis class. Furthermore, previously I mentioned about the embedding of H11, the Doppelt 11 class, Doppelt 11 cohomology to the second singular cohomology. Here we need the partial bar lemma. And for Fujikis class, it still holds true, which implies that we can freely use the equivalent Born-Chen, partial bar, Doppelt, partial bar, and the RAM D cohomologies. And moreover, the Horsch decomposition holds true, so we can decompose the singular cohomology. In particular, we only use the following injection, which embed the 1,1 partial bar to the H2 of the singular cohomology. Okay. So let us summarize this part. So which says that the non-Kähler locus of a big class is may not be auto invariant, but auto Tor invariant, the compact complex space in Fujikis class. It can be singular, of course. The proof is simple. You consider any G in auto Tor and the G pullback action. By definition, if the pullback action on H2Q is identity, then so is the action on H2R. Then by this embedding, we see that the pullback action on the 1,1 class is identity, and hence it fixes the big class alpha. So this non-Kähler locus is auto-Tor invariant. Okay, now let's end of the proof by using the previous results. So we first let G be auto-Tor. And by Minkowski, we see that we only need to show G is Jordan. And we denote by Z the non-Kähler locus of alpha. And we do below replacements find many times. Because now Z is not Kähler, may not be Kähler, so we don't know whether we can use the previous result about the Jordan property of auto XZ, but we can do several replacements. First, if Z is smooth, a compact smooth connected Kähler, then we do nothing. We stop. If Z is not connected, then we replace G by a finite index subgroup, preserving all connected components of Z, and replace Z by arbitrary one connected component. And if Z is not smooth, then we simply we do not do resolution here. So we simply replace Z by the singular locus of Z. Okay. And if Z is smooth connected but not Kähler, then we pick some big 1,1 class because it lies in the Fujikis class. So we can find some big class beta and replace Z by the non-Kähler locus of beta and G by the following subgroup, which has the quotient having bounded finite subgroup because it is the rational representation on the second singular cohomology of Z. Okay, so this is a so this replacement is okay. So eventually, of course, this replacement may not be satisfied in one step. So you see, if we replace z by the non-killer locus of beta, it may if z is smooth, this part may not be smooth. So we need to run step 1 or step 2 several times. But each time the dimension decrease or the kinetic components decrease. So with finite many steps, we can end up with step 1. So now we only need to show that our new G is Jordan, and it is because.
Sorry, can you comment? I think that step 4 is the main step.
Yeah.
How did we know that Z doesn't coincide with X? Maybe it's like totally elementary, but
Z does not what?
Coincide with the whole X.
Coincide with whole X. What do you mean by coincide?
It's some subvariety of X.
First Z is a subvariety of X because we take this one. Then if Z is not if Z is not killer, then we pick the we take the non-killer locus of the big class of beta in Z. So it is a subvariety of Z. So again, a subvariety of X. Okay.
So here we use that a non-killer locus of a big 1-1 class is always a proper subvariety, right? It cannot coincide with the whole Z.
This big 1-1 class is for Z, not for X.
Okay, then I have a question. So we used to know that there exists a big class on X. That's fine. How do we know that it exists on Z?
Because we use this fact. Every closed analytic subvariety, and we don't use this here. Every closed analytic subvariety.
It's also not very far from Keller.
Yeah, so this is very important here. Yeah. Okay, good. There are no problems. Okay, so now our new G, we need to show, because each replacement satisfies our good. So we only need to show the new group G is Jordan. And it is this because our new G still fixes our new Z. So it lies in the auto XZ, but our new Z now is already compact, smooth, kinetic killer. So by previous result, this is a Jordan group. So eventually we show G is Jordan, and hence the auto tau X is Jordan, and hence the 4 automorphism group is Jordan. Okay, so this is the end of the proof and also end of my talk. Thank you.
Thank you very much. Are there any questions? Let me ask a question then. So it will be partially a reiteration of the question asked by Yuri in the middle of the talk. Suppose that X is not just from class C, but is Moishe zone. I understand that some of the theorems may be are not necessarily simplified in this case, but is there at least something in the proof which becomes simpler if we restrict to the class of Moishe zone varieties instead of class C?
No, I guess maybe if you want to simplify the proof for the complex surface, right, and motion is threefold, right? These two cases, maybe you can use this one. For example, if it is a for the surface or threefold, maybe you can use the MRC or the Albanese. You have the non-trivial fibration. Then you can find some. If it is possible, if you can find some invariant curves. For example, some compact surface may have with algebraic dimension 0 may exist some curves, but only find many. Now, these curves are always invariant or periodical. So in this way, you can apply this result because curves are always projective. So by using this, you can show it is Jordan easily. Yeah, this is one
Yeah,
simplification. Maybe.
this is clear. But this is a kind of a first half of the proof where you, yeah, I mean the second half of the proof when you start, yeah, starting from your main theorem, when you start working.
I think this part is similar to Moshism. I don't think this makes any easier. Yeah, Fujiki is like Moshism, I think. Big class, just a big line boundary and big class makes no much difference, I think. Yeah.
I see.
Yeah.
Any other questions?
So I have a question about Fujiki-Lieberman theorem. So Fujiki-Lieberman theorem is also true for complicated manifolds with a big class. So is it possible?
No,
Yes.
they are not true for big class.
So
they are not known at least, because yeah, because big you have small part you cannot control in the duality space. This is something like the Hilbert scheme parameterized by you can bounded by the Hilbert polynomial, but you at least need to fix one ample line bundle, but or a positive form. But if it is only big, I don't know. I don't think it is that easy.
Because I think there's a result due to Ding, Hu, and Zhang showing that the Fujiki-Lieberman type result is
but this requires first you have a killer form, then you can apply it to the big class.
Yeah, so it holds for
so this is true for big class, and this is true for big class unless it has another killer form omega prime. First, you need to have a killer form omega prime. Then you can apply it to any big class.
Yes.
Yeah.
So do you expect? Yeah. So do you expect that by taking Kähler equivariant Kähler resolution of this of X, you can deduce the Fujiki-Lieberman result from the Fujiki-Lieberman upstairs?
I think they are somehow equivalent, somehow, but I don't have a rigorous proof. They are quite, yeah, because if you have the equivariant resolution here. This is not a key point because I don't expect I don't expect the existence of equivariant resolution because sorry, where is it? Oh, here. Okay, this question, right? And this two questions. You mean these two questions, right?
Yes.
First, if you have this equivariant, then I guess they share the same auto zero. They share the same auto zero. So if this equivariant holds, then you can have the Lieberman-Fujiki's result. Yeah. By showing that the auto zero x tilde equals to auto zero x.
Yes.
Okay. And that's
also.
Yeah, but probably, yeah, but after blowing up, this will
but this is too strong. But this question is too difficult. Because as I said, the key step of showing that Fujiki's class admits a killer model is by blowing up the ideal sheaf of this one, by blowing up this ideal sheaf. But this ideal sheaf may have multiplicity, although you can show some equivalency on the non-killer locus of alpha, but you cannot show the invariancy of this ideal sheaf. This is, for example, you take f1 to be x equal to 0 and f2 equals to some y. X, for example, the point is the original over a plane. It is the original point 0, 0, but its defining equation may not be preserved, like an x y squared. This is the x and this f2 is y squared, but the x y are not preserved. So the ideal x y squared is not invariant.
Sorry, I have missed it. Yeah. So you have some invariant subscheme inside your.
Yeah, you can. This is the reduced part of the zero of the ideal sheaf. You can show the invariance of this one, but you cannot show the invariance of this ideal sheaf. So this is the main difficult point.
So yeah, and can I then repeat the claim? So here, yes, here it is necessarily reduced by definition, and the theorem about yes. So you know that there exists equivalent reduced subscheme. You don't know that there exists an equivalent G invariant.
Yeah, I don't know. I cannot show.
And
yeah.
to obtain a Keller resolution, you really need to blow up the non-reduced one.
Yeah, the proof is first. Indeed, the proof is a little bit complicated. First, you need to blow up the ideal, but the blow up the ideal sheaf is then you create a very strange, a very singular one. Then you need the choice lemma. You need to do further blow-ups. Yeah, but if of course, if the ideal is good enough, which is just the non-Keller locus of this, and this singularity of this one is also good, then the equivalency, I think, it exists. The equivalent block exists. Yeah.
And can it really be? So can it, in fact, be non-reduced? I mean, other examples of some non-reduced behavior here?
I don't know any of this. Sorry, I don't know any example of the ideal sheaf being non-reduced. Sorry.
Because just a moment. Because
yeah, I don't know whether I don't know any non-Keller, but in Fujika's class, but with the ideal sheaf being non-reduced. Sorry, I can't.
It's the same as a base locus of some linear system. It can be very complicated. So
of course, but you can always pick some good good linear system, right? Of course, you can choose artificially some very bad line bundle, of course, but the existence of some good line bundles with reduced structure of the non-Keller locus is not known. Yeah, this is a little bit difficult. Yeah.
And so, and the singularity of T. So T is a current. The singularity of T. The notion of singularities, singularity locus of T or singularity locus of phi, the plurus subharmonic function. Do the singularity loci have a skew structure, or they are automatically reduced by definition?
Reduced, only sets.
They are just sets.
They are just sets. Yeah.
I see. Any further questions?
So let me make a comment to the question of Yuri and Constantine. So in the motion case, you take a non-Keller locus. So the locus is still analytic subset. Maybe can you prove this locus is also Moishian? Then it helps. It's a Fujiki C class. If X is Moishian, then can you say this locus is also Moishian? Then it helps maybe.
I don't know, but it's
dominated by some projective. It's dominated by projective, right? So that means
dominated by projective. That's right.
Because it take a blow up. So that means it's a kind of Moishian.
As long as if it is dominant by projective, then it is Moishian.
Yeah, sure. Yeah. So it's yeah. In the Moishian class, everything is Moishian.
So the image motion should be motion, right?
Yeah,
of course.
Image.
And then it may help. So the locus is not bad, it's motion. So
but the proof are still the same, I think.
Still good.
Yeah, still. Yeah, unless you choose. Yeah.
The other remark is that you asking this non-K locus. So in algebra geometry, it's just a non-ample locus. So the non-ample locus is numerically defined. So it's B plus. the
B plus some small ample divisor. The base locus of B plus some small ample divisor by taking limits, something like that.
Correct. So non-Kähler is just non-ample locus, so it's numerically defined. So it's the current minus small epsilon time Kähler form. So it's you know, anyway, it's the same analytical algebraic. Yeah. So it's fixed by, you know, it's defined by the class, not by this form. So.
But they use the notation, so I keep this notation. They use the notation for alpha instead of the bracket of alpha. But indeed, it is defined for the class. Yeah. For the definition, you can see it easily because it takes the intercept of all the currents in the.
This equality important. The equality say that it's invariant. Yeah. Without this equality, you don't know this.
Thank you for the comment. So any other questions or comments? If no, let's thank Sheng again.
Okay, thank you very much. Okay, I will stop the sharing. Can I stop?